The aim of this project is to solve the mountain car problem using the SARSA algorithm. Mountain car is a classic test domain used within reinforcement learning and can be easily modeled. The problem takes place in a simple landscape represented by the blue graph. On the bottom of the valley sits a car, represented by the red dot. In a classic problem, the goal is to drive the car to the top of the hill and reach the goal state, represented by the green flag. The driver can choose from a set of 3 actions. He can drive forwards, backwards, or choose to do nothing. Unfortunately, the car doesn't have 4-wheel drive, meaning it cannot drive directly up the steep slope. Instead, the car has to gain momentum by rocking back and forth, thus gaining the velocity needed to reach the goal state. The aim of the mountain car problem is to train a reinforcement learning agent to learn the correct set of actions needed to reach the goal state. For this project, we are utilizing several of the techniques learned previously in the course. In order for the reinforcement learning system to be able to efficiently learn which actions lead to a reward, it may not be sufficient to use a simple temporal difference model like TD0. When using TD0, the model is only able to backpropagate future rewards one step at a time, which makes it an inefficient algorithm for problems where the episodes can be relatively long, such as the mountain car problem. In contrast, when we used Monte Carlo tree search in Project 2, all the visited states in the current episode were updated with a constant reward upon reaching an end state. For this project, we decided to use eligibility traces, introduced in Project 1, which unifies temporal difference and Monte Carlo methods. The rationale behind this choice was that combining eligibility traces with SARSA would make the learning more efficient. When using eligibility traces, previous states are updated with a progressively smaller reward the further back you go. In Project 1, we implemented an actor-critic network, wherein the actor holds the policy and the critic holds the value table, implemented as a function approximator, a neural network. Our implementation of the SARSA architecture is based on our critic network from Project 1. Instead of separating the actor and critic, they are combined into a single agent for prediction and control. Unlike the critic, SARSA learns the values of state action pairs instead of only looking at the states, by using a function approximator Q. It is an on-policy method, which means that the values in Q are updated based on the states generated from Q. This project differs from previous projects as it employs a type of coarse coding named tile coding. The mountain car problem is represented as a simple 2-variable state consisting of the car's position along the x-axis and the velocity of the car. Imagine the natural representation of this state in a continuous 2-dimensional space. The tile coding representation of this state is made up of features corresponding to squares, or tiles, as illustrated by the blue grid. If the state is inside a tile, the corresponding feature is set to 1. Otherwise, the feature is set to 0. The receptive fields of the features, the tiles, are grouped into partitions of the state space, referred to as a tiling. This is represented by the blue grid as a whole. Tile coding transformed the state space from continuous values to discrete values. The number of features passed onto the neural network depends on the number of tiles inside the grid, as given by tiling 1. To utilize the strength of tile coding, multiple overlapping receptive fields are used. Here, 3 tilings are used, each one offset by a fraction of the tile width. The state falls in exactly 1 tile in each tiling. These tilings correspond to 3 features becoming active when a state occurs, as given by the features list. We divided our code into 2 main components. You have the simulated world, which holds the mountain car logic, similar to that of the previous projects, and then you have the reinforcement learning system, which holds the tile encoding, the SARSA algorithm, and the agent, which has the policy function and the neural network. Both of these components receive their settings from the parameters file, which works as an interface for the system. Here you can see a simulation of the system after 10 episodes. The agent performs rather poorly, which is expected, as it hasn't learned a winning strategy yet. This is the result we got after 100 episodes. The agent performs much better now and is able to reach the goal state in just a few moves, indicating that the system is able to learn a winning strategy. Our system employs an epsilon greedy strategy, yielding a high degree of randomness during the first 2 episodes. As we decay the epsilon, the policy becomes more greedy. The agent is given a reward of -1 for each move and +1 when the goal state is reached. The agent is therefore highly dependent on randomness to learn the correct strategy. As illustrated by the plot, the agent's performance is poor during the first 2 episodes. Once it reaches a goal state, as seen around episode 20, it starts to learn the correct strategy. When this is done in combination with more greedy actions, the system performs better.